Hello and welcome to the lecture Variational Autoencoder Part 2. In this lecture, we first introduce the variational inference and how this variational inference is helping for modeling the variation autoencoder. Then we discuss the loss function of variation autoencoder and we conclude this lecture by discussing the different application of variation. So, in the last class, we have seen that in our variational autoencoder model, we have to determine p theta x, and this is integral of p theta x given z, p theta of z, and dz. Now, this thing, this pg, this is basically, we said that the prior distribution or latent distribution, and we assume it is a very simple distribution, that is Gaussian distribution. So that is okay. Again, this p theta x given z, that is also a neural net decoder network. So that is also no issue, that there is no issue here. But what we have find in our last class, that the z, this z is, there is a so many, can say, attributes z. So there is a lot of integrals here. So that makes this thing intractable. So this integral is intractable due to this z. Now in variational inference, we want to solve this, or we can say using variational inference trying to solve this problem. So what we are doing here, instead of computing this true posterior, that p of theta z or z given x, and say this is the posterior, we approximate with a simpler distribution, that is q phi z of given x. Now you see this p theta z given x, this is the posterior. This thing we being approximated by a simpler distribution, that is q phi. But this phi is the encoder parameter. Usually Gaussian with mean and variance predicted by neural network. Now here this approximation going to solve this. And this q phi z of is basically encoder in variation. So we get that we are going to find the posterior of this p theta z of x, as we have discussed earlier, and then we use q phi zx, because p theta x is anyway tough to compute. So that's why we go for this kind of encoder parameterized with phi, that is also a neural network, and that usually Gaussian mean with variance predicted by a neural network. So this is the encoder in variation. Now try to understand what does this mean. So to solve this intractability, we like to introduce a new approximation function, that what we have discussed. Output, what is the likelihood given input x, q phi z of given x, parameters by phi. Now here you can see that this probabilistic encoder, now you see we start from x, so this is our data sample, and this q phi x is going to sample or going to produce z, this latent distribution, using this probabilistic encoder. So now this is going to as a solution of this interactability. Now, the conditional probability P of theta of x given z, that this defines a generative model, because this is probabilistic decoder. This is basically a kind of generator. That's this P theta x given z is a kind of probabilistic decoder, which is known as probabilistic decoder, that we already understood in the previous discussion. So, approximation function z q phi z given x is a probabilistic encoder. Now, this you can understand. So, this is the statistical understanding of encoder, better to say probabilistic encoder and probabilistic decoder of variational encoder. Now, here the similar image been drawn, that you can see first from as an encoder this, the saffron line, that q phi z given x. This x is basically the data set, and this phi distribution is Gaussian distribution. And now that this when we get this z, then we use this probabilistic decoder p theta x gives, that will reconstruct x. So, this blue line is basically the reconstruction phase or decoding phase or generation, and this p of z or p theta z, that this is a simple Gaussian that we have discussed earlier. Okay. So, this is the basic formulation of variational autoencoder, that this interactability is solved by the variational inference. So, given this x, now this x is what? X is basically your input data sample, real data sample. That probabilistic encoder produce these latent vectors or latent distribution, and this from this distribution is probabilistic decoder sampling and reconstruct, not reconstruct. That is very important to understand. We are not reconstructing here. What we are doing here, we are generating new samples, and that samples are not within this given data sample. That is something new, but it's a very similar that follows the similar distribution. That is the main agenda, main issue of the generative model. Now, with this concept of variational inference, we look back our previous slide of variational autoencoder. Some terms maybe we can't understand that time very well. Now, what it is being said there? The autoencoder is trained or improved to regularize the latent space so that it can be used as generative model. Now, what do we mean by regularizing the latent space? That rather generating some values, now our probabilistic encoder, which is the new thing in variational autoencoder over the normal autoencoder, that it to produce the distribution. So, this encoding, so what it is been written, this is achieved by encoding the input as a distribution over the latent space. Previously, that there were some values. Now there is a set of distributions. It's rather encoded as a single point or single value, and that is the main thing, major thing we have to understand. Okay. Now, from this distribution, when we get this distribution, we can sample it by our probabilistic decoder, and from this sample we generate our data, new data. Now these new data or new samples are not part of this given data samples, and that is the major difference variational autoencoder from the normal autoencoder, and which essentially make the variational autoencoder generative in nature. So what is the error calculation? The error is basically that how the generated data, that generated data is also belongs to some distribution. Now how this distribution is similar to the given distribution by means of this set of samples, that we have to going to minimize. That we will see later how. That loss is going to optimize these two neural net. So essentially the goal of variational autoencoder is to find a distribution Q phi zx, that is the encoding part of some latent variable z, which we can sample from z which to Q phi z next to generate a new sample x bar, that is p. Now the thing is that here what is major things been achieved by this our concept of variational inference, that in spite of generating the values, we are generating the sum of distributions, and from this distribution this decoder samples and then generate the new data. Now take an example and check. Here in this image, this is a dog image. Now this probabilistic encoder, this is simple autoencoder. This encoder is going to use this eye, ear, nose, color, these latent attributes. Okay. Now these latent attributes, what we are giving, these are values actually. Okay. Now these values are being okay. Now this decoder, it is not the probabilistic decoder, that it just given the this image, this produce this. This is input x, this produce the latent. Okay, and this decoder is also not probabilistic decoder. It basically given these values, latent attributes values, try to reconstruct the input. So here important is that the image is being reconstructed. So an ideal autoencoder will learn the descriptive attributes. So an image is being represented by some useful or meaningful attributes like eye, ear, nose, color of these images, and learning these attributes. Now one thing also you can notice here, this attribute space is much lower than the actual image space. So here it is a dimensional reduction also. We try to understand an image or try to represent image by this attribute, or we can say more simplistically by a feature space. And features are these basically the values. Those are feature values kind of thing. And giving these feature values, we can find this or reconstruct this. There is definitely some image. Here we put some black dots to find out these two are not same. There is some reconstruction error. Okay, but most importantly, in this example or in the case of autoencoder, these attributes are described with a single value. That is most important to understand. Now come our variation. Here also this encoder is now this is not normal encoder, it is probabilistic encoder. Now how it is doing, it is taken an image and now rather generating values like autoencoder, normal autoencoder, it generates the distributions. Okay, and this decoder is basically sampling the data or samples from this distribution and produce this. Now this is not the image that is present here, this is a new image. Maybe the attributes space are same, but it's a very similar kind of image, but it is a different image. So in variational autoencoder, each latent attributes are now represented with a probability distribution like this. These are the latent attributes and these are the probability distribution. So the decoder now can sample a value from this distribution to form a similar looking image which is not present in the training data set. That is very important, and that this time several times we are saying. It is the major concept, major understanding in variational autoencoder. It is not reconstructed image, unlike autoencoder. Rather, it's a new image, generative in nature, with similar attributes. Now, that is the major understanding. Then we'll see how actually the mathematics behind this to understand this kind of laws and how all these things will come. But if you understand this is properly, you can understand the thing very clearly. Now we are going to understand the loss function of variational autoencoder. So the loss function of VAE has two main components. One is reconstruction loss, and is regularization loss or KL divergence. So together they ensure the model both reconstruct the data well and learns a smooth latent space. That we'll see in our next 2-3 slides. That what are the mathematical formulation or what we means by reconstruction of data and learns the smooth latent surface. So in expression or mathematical expression, if we write for the objective function of VAE, it is this expectation of Z belongs to Q phi Z given X, log of P theta X Z, and minus of this scale divergence between these two spaces. So it's smoothed out. So it's basically the regularization in this latent space. So this is the regularization term, and this is the reconstruction part. How data are being generated which is more similar than the real data set. Now this is the objective. So definitely loss is the negative of this. So if we write the negative of this, so this thing, and this is basically written as the loss of variation. So the basic thing that we're going to understand here, what is the mathematical formulation of this loss function, from where we get these expressions. It is bit mathematical, but I think we can understand it clearly. Let's try. Now first we understand what is the loss function, from where this expression comes, and we see this loss function called ELBO, evidence loss lower bound, evidence lower bound is called ELBO, will come later. What is this? Now first of we read out so that we understand what we actually want to do here. The estimated posterior, that Q phi, that first we understand these terms. What are they? should be very close to the real one, p theta z x by z. We can use this Kullback-Leibler divergence to quantify the distance between these two distributions. So these are two Latin distributions. So actual this is the Latin distribution, and what Latin distribution we are by encoding we are getting this. So and this if these two distributions are very similar, then definitely we smooth out the Latin space. So KL divergence measure how much information is lost if the distribution y is used to represent x. So basically that what is the difference? In our case, we want to minimize this scale divergence between q phi zx, this distribution, and p theta z given x, the q phi z given x, and with respect, because this is our parametric. This is the encoding parameter. Okay, let's try to expand this. So if we expand that this scale divergence term, then it is the integration of q phi z given x log of q phi z given x by p of theta z given x dg. So this is now we can do one thing. Since p theta x is multiplied in numerator as well as denominator, so it becomes the same thing. So we do for some mathematical convenience. Now what it effectively comes, then it is this integration of q phi zx simple and log of z given x p theta x by now p theta z comma x. This is a joint probability because this is similar to this. This p theta zx can be written in place of p theta z given x p theta x because of this reason. Now what we can see from here, we can see that this is basically that this particular thing, that log of p theta x, we separate it out. So there's two things we find. Q phi zx is similar, and log of p theta x we can consider plus log of q phi z by p theta zx. And now if we do this integration here, now this integration log of p theta x and q phi zx dz plus integration of q phi zx of q phi zx by p theta. Just do it. This is very simple. Anybody can understand. Okay. So what it turns out, that since this is phi, this is, you can say this is z, there is nothing z here, so we can dot in outer. So log p theta x integration of q phi zx dz and plus integrate of q phi zx log of q phi z p theta zx dz. Now what it look like, that q phi zx dz plus that was. Now what we'll see, now q phi zx dz, this is basically 1 because z dz. So if it is 1, then it is become, this term become only, this is 1, so it is log p theta x, and rest is there plus integration of q phi z given x log of q phi z dz. Now again we extend this p theta zx. P theta zx we can write p theta zx given g is p theta. Okay, dz. Now if we write this, we can write this expression, that log of p theta x, and you can say this is the expectation z belongs to q phi zx log of q phi zx by p theta c minus log of p theta x. That is a simple term from this simple statistical theory. Now what is this? So this is basically this Leiber-Coolb vertex. So KL divergence between Q phi z given x and P theta of z. This two. And this expectation term of these things. So ultimately it is written that the total term boiled down log P theta x as d of this scale divergence between Q phi z given x and P theta z minus it this expectation of log P theta. Now what is this? Now we start initially from this divergence Q phi z x, so we can just write Q phi z x P theta x. Now it is log of P theta x plus this d of KL Q phi z x and P theta z. This is the KL divergence between this and this term. So now if we just change these things, log P theta x minus this dkl Q phi z x P theta z x, this we can get this term. Okay, now we'll see what we'll get. We get log of P theta x minus d of k, this KL, that means this KL divergence between Q phi z x P theta x. What this is we required, and it is right, that expectation of log P theta x minus KL divergence of Q phi z given x. Now what is LHS of this? That is very important. The LHS of this equation is exactly what we want to maximize when learning the true distribution. Why? We want to maximize log likelihood of the generating real data. That is log P theta x. That is the reconstruction kind. That we want, that what we are generating that looks like the real thing. And also minimize the difference between real and estimated posterior distribution. So the term this DKL, that is this scale divergence, works like a regularizer. So this term. Note that P theta x is fixed with respect to Q phi. So the negation of the above defines logs of V. Now you see here we can say that here we started from, we try to find out this minus Ez Q phi z x log P theta x dl. That we want to find. Now you can see this minus log P theta x plus L Q phi z x P theta x. Same thing. You see? That is the basic P theta x. See? And now we put it this term here. So minus that expectation of g phi z x log P theta x comma x by z, x given z, plus this the distance between this, the scale divergence between Q phi z x P theta z. Exactly what we have written here, that this is our loss function. Now we understand that from where we get this loss function, and this from where we can this theta star and phi star from, we are minimizing this loss, we can get this theta star and phi star. So that is the basic understanding of this VAE loss, from where it is being. So there is some bit mathematical, but we have to mathematics to understand from where this loss function comes. Okay. Now what is elbow? Here we can see this is our loss function, and this is minus e of x log of p theta x given z, and this is divergence, scale divergence between q phi z given x and p z. In variational Bayesian methods, This loss function is known as variational lower bound or evidence lower bound. The lower bound part in the name comes from the fact that KL divergence is always non-negative, and thus minus this L, the loss is a lower bound of log p theta x. That's why it's called lower bound. Okay, so minus of is it's always less than 0. That is the name coming. Therefore, by minimizing the loss, we are maximizing the lower bound of the probability of the generating the real data samples. That is the basic understanding of this. So, what we have understood that this loss function include this KL divergence. Why KL divergence is included here or used here? It regularizes the latent space and definitely prevents overfitting. It ensures smooth interpolation and makes sampling much easier or make it possible. So that is people can why KL divergence. So this is the major reasons that was our main concern. So we have to regularize latent space so that we can sample it out, so that our autoencoder become the generative in nature and now become variation autoencoder. Okay, so we concluding this variation by saying that this what are the basic application. Nowadays image generation is a huge thing, as we have discussed about the session, that there is a lot of application in image generation, because in supervised learning paradigm there is a often data scarcity, annotated data scarcity. So this VA, since it is supervised, so we can anomaly detection, drug discovery. So there is a lot of this kind of synthetic image generation, data generation is required. Representation learning is also semi-supervised learning. These are the applications areas. So in our VA, in this particular lecture, we understood what is variation inference. We then understand the mathematical formulation of loss function, and we explain what are the applications of the VA. In our next module, we are going to discuss the diffusion model part 1. Thank you very much.